Okay, so that's going to equal, I'm going to have to write smaller now, 9 over 4 power of 6 plus sine, 1 over 6, sine of pi, because 6 and power of 6 just cancel out and leaves you with pi, minus, I might as well just make that 1, 9 over 4, negative power over 6, plus 1 over 6 sine of negative pi. Ooh, that was close. Okay, so we know sine of pi and sine of negative pi is 0, so that those two will actually disappear. So we end up with 9 over 4 times pi over 6 plus pi over 6, which is 2 pi over 6, which is pi over 3, but we'll leave it that way. Just, I guess you could have simplified it a little bit. I'll leave it like that. Okay, so if we, that'd be 9 pi over 12, which is just 3 pi over 4. Okay. So that's the area of one of the petals. All right. Any questions on that one? So really it all kind of revolves around the formula. All right, so for arc length, we'll actually skip the proof, but I will provide it in the notes if you're interested. It's just, you don't really need it. Oh, you want still writing? All right. Arc length and polar coordinates. Okay, so that's just the length is equal to, from alpha to beta, the square root, well, instead of f prime of theta, well, you can do it either way. I'll write both. F prime of theta squared plus f of theta squared. Clean that up some. With respect to theta, or you can write it from some alpha to beta, derivative of r with respect to theta squared plus r squared with respect to theta. Pretty much same thing. But that's if r equals some function of theta. Clean that up a little.
Can you zoom in on that at all?
Which one?
The top part.
This one?
Yeah.
I'm scared to zoom in because this thing may stop working.
I'm sorry, but I just blind.
F prime
Which one?
of theta squared.
Oh yeah, f prime of theta squared. Which part
I'm
did I
just
lose you on?
making certain I didn't rewrite anything badly is all. Okay, thank you.
Not a problem. Have to do manual zoom so this thing doesn't mess up on me. Burning another 10 minutes trying to refocus it. All right, so let's say, for example, find the exact arc length of r equals 3 sine of theta. Okay, so if we wanted to just look at it graphically, let's say 3 sine of theta. How's that sine there? Of course, that's from 3 to negative 3. And this is 3 sine of theta. Okay, so we don't want to know the arc length of the entire thing going on forever. So really, we just want to know the arc length from here to here. Because if we want to know more, we can just multiply it. So if we want to know, once we find the arc length here, we can just say, okay, what's the arc length from 0 to 2 pi? We just double this. And then arc length from that, and we just keep on multiplying. So really, we just need to find here. Okay, so where it goes from 0 to 0 again. So we know that sine, well, 3 sine of theta equals 0 when theta equals, well, you can say 0, pi, 2 pi, et cetera, and so on. 3 pi, and so forth and so on and so on. Okay, so really we'll just find it between 0 and pi. That's really all we need. Okay, so the arc length, so we use 0 to pi. From 0 to pi times the square root. Oh, actually, it would help if I had my r and dr d theta first, so we'll do that first. Don't have to do it first, but just makes sense. Okay, so we know that r is equal to 3 sine theta. And derivative of r with respect to theta equal to 3 cosine of theta. Okay, now we can just plug it into our formula. So the length is equal to, from 0 to pi, the square root of 3 sine theta squared. Well, it doesn't really matter which one you do first, but I'll stay with the formula. Plus r squared, so 3 sine of theta squared with respect to theta. Okay, so that's just going to equal from 0 to pi, 9 squared, well, 3 squared, which is 9, cosine squared theta, plus 9 sine squared theta with respect to theta. Okay, so if we actually factor out a 9 from both of them, oh. Okay, so from 0 to pi, we actually can factor out that square root of 9. Cosine squared theta plus sine squared theta. I'll just put that. Oh. All right, so that actually gives you 3 And we know cosine squared plus sine squared is equal to 1. With respect to theta. Okay, which gives us 3 theta from 0 to pi, which of course gives us 3 pi minus 3 times 0, which is just 3 pi. Now, if we want to know it from 0 to 2 pi, we just get 3 pi times 2, then 3 pi times 3, and so forth and so on. So that's why we only need just the one section of the arc length. All right. Any questions on that one? All right. Okay, so lastly, we're going to go over L'Hopital's rule. Now, some of you may have had it in Calc 1, some of you might not have had it in Calc 1, depending on where you had it, but just to be on the safe side, I'm going to go over it again anyway. I know in some schools they offer it in Calc 1, in some schools they offer it in Calc 2, so we'll see. It's better safe than sorry. And L'Hopital's rule just makes life so much easier. All right, oh, you were still writing? Nope. Okay, so let's say if we let, clean that E up a little bit. F of x and g of x represent differentiable functions. Where, of course, we know that g prime of x can equal 0. I guess you could say g of x can equal 0. Now, if you happen to get the indeterminate form, let's say f of x over g of x as x approaches some value of c, and you end up getting 0 over 0, just through direct substitution. Then the limit of f of x over g of x as x approaches c is equal to the limit of f prime of x over g prime of x as x approaches c. So in other words, just apply the derivative to both your numerator and denominator.
Isn't it also applicable to infinity minus infinity?
Yep, it applies to infinity over infinity, infinity minus infinity. We're going to go through all of those. Yep. Also applies to infinity over infinity, negative infinity, or positive infinity over negative infinity, and negative infinity over negative infinity. So that's when you don't have to do any type of manipulating or anything else. All right, so let's say, for example, we have the limit of 2x squared minus 2 over x plus 1 as x approaches negative 1. Okay. So if you just plug in negative 1, you get negative 1 squared is 1. So you have 2 minus 2 is 0. Negative 1 plus 1 is 0. So you get 0. Okay. So you have the indeterminate form, which means you can use L'Hopital's rule. Okay. So this means find the derivative of both your numerator and denominator. So it's the limit derivative of 2x squared minus 2 over the derivative of x plus 1. Which gives us the limit as x approaches negative 1 of 4x over 1. Now you can just use direct substitution. So you have negative 4. Right. Same thing if you had infinity over infinity. So if you have the limit of 3x squared minus 1 over 2x squared plus 1 as x approaches infinity, if you just plug in infinity, you get pretty much 3 times infinity, which is still infinity. Infinity minus 1, you might as well say that's still infinity. So you have infinity over infinity, which you can just apply L'Hopital's rule. Okay, so that means you get the derivative of 3x squared, which is 6x, over the derivative of 2x squared plus 1, which is 4x. Once those x's cancel out, limit as x approaches infinity of 6 over 4. It doesn't matter what it's approaching, it's still just 6 over 4, which is 3 over 2. Any questions on that one? All right. Everyone's still writing. Okay. Now, if you have, let's say, say 0 times infinity, infinity times infinity, or if you have 0 to the power of 0, or infinity minus infinity, it will be necessary to use L'Hopital's rule. Okay. So in other words, it has to be 0 over 0, or infinity over infinity, or negative infinity over positive infinity, or any variation of those. So it has to be in the form 0 over 0, positive negative infinity over positive or negative infinity, and some combination of the two, to use L'Hopital's rule. All right, so let's say, for example, what if we wanted to evaluate the limit of e to the power of negative x times square root of x as x approaches infinity? Okay, so we know that e to the negative x is just 1 over e to the x. And if you just made x get bigger and bigger and bigger and bigger and bigger, 1 over e to the x is just getting really, really, really close to 0. Let's say 1 over e to the x times square root of x, just to rewrite it. But if you plug in square root of infinity, that's just going to keep getting bigger and bigger and bigger and bigger. So you really just end up with 0 times infinity, which means you can't use it yet. Okay. So you actually can convert it as x approaches infinity, square root of x over e to the x. Okay. Now without that negative, if you plug in x getting bigger and bigger and bigger and bigger and bigger, e to the x actually approaches infinity. And square root of x, once you plug in x and it's getting bigger and bigger and bigger, it's just going to approach infinity. Clean that up a little. Okay, so now we can use L'Hopital's rule. Uh-oh. Okay, so that means you have the limit as x approaches infinity of 1/2, well, square root of x is just 1/2 x to the negative 2 over e to the x.
X is the negative 1/2, isn't it? Not negative 2.
Negative 1, oh, well, I put 2 up there, negative 1/2. Still have my Monday brain.
Doesn't help that he basically had like a week off
Oh
of
my
necessarily teaching because it was the test and then a day off.
Yeah, that didn't help, but have to wake up. All right. So from there, now, might as well rewrite it. Let's say 1/2, 1 over square root of x divided by e to the x. Or even if you wanted to, you can write it as x approaches infinity, as the limit of 1 over 2 square root of x e to the x as x approaches infinity. Which means as x gets bigger and bigger and bigger, that gets closer and closer and closer and closer to 0. So you end up with a limit of 0. All right. Any questions on that one? All right, so I'll do one more really quick example. Oh, that one's not quick. Yeah, this one's a little bit lengthy and it'll chew up a while, and I don't want to hold you completely over, so I'll add it to the notes. Yeah, I'll add it to the notes.